Hello everyone. Welcome to today's data learning seminar. So today we're very happy to have Alexander Kuhn-Regnier from the physics department at Imperial College. And he will talk about the importance of vegetation and drought for global fire prediction. So Alex, I will leave the audience with you.
All right, yeah, thank you for the introduction, Sibo. So yeah, as mentioned, my name's Alex, and today I'll be talking about the work I did analyzing global wildfires empirically. So this was part of my PhD, specifically the first part, and I am currently, well, as I said before, writing up the thesis, but what this work kind of led into then was an improvement in the INFERNO fire model, which is something that I'll briefly touch upon as well. So first of all, what you see in front of you now is a map of mean burnt area at the bottom. And this is essentially what we're trying to predict. I've also plotted time series of burnt area in red and the measure of vegetation greenness, FAPAR, in green, for two locations. First of all, Northern Africa and Northern Australia, as you can see there. And what's apparent is that the burnt area is concentrated around several months, which is usually referred to as the fire season. And the vegetation reaches a peak sometime before that fire season. And it is this seasonality, this temporal offset, that we wanted to capitalize upon and understand in greater detail. So throughout this talk, I'll begin by talking a bit about the context of wildfire, the current developments at Imperial as well, the goals of the different empirical analyses I'll talk about later, how we actually carried those out, i.e. the different machine learning tools, the results of these analyses, like which of the variables we included were most important and which kind of underlying relationships we found. And then finally, I'll talk a bit about how this was then applied to the INFERNO fire model. So in terms of public perception of wildfires, I feel like there's recently been a shift with increasing awareness about, first of all, the impacts of wildfires and the occurrence of very large wildfires, but also about land management and fire management, for example, the controlled burning you see in the center here. And this is something that is perhaps a shift, especially in Western cultures, where originally European fire management relied very much just on suppression. And now we're seeing a shift towards more sort of integrated fire management, going back to more traditional practices. And these kinds of practices, they acknowledge that there's a need for fire. And this is just one of the reasons for improved understanding of fires. And especially given the changing climate and future impacts, that's another reason we want to further understand fire impacts. And the empirical analyses I'll present soon are one way of doing that. At Imperial itself, we have recently seen the establishment of the Leverhulme Center for Wildfires, Environment and Society, which is a large center, a group of PhD students, postdocs, etc., focusing on fire science in all regards, ranging from socioeconomic issues like health impacts, all the way to fire spread modeling. And the INFERNO fire model, which is part of Jules, itself part of the UK ESM model, was also developed at Imperial some years ago. And this is a very coarse scale global fire model meant for predictions on decadal or longer timescales. Again, something I'll touch upon later. In terms of the basic requirements for fire, we of course need something to burn, the biomass. We need oxygen and an ignition source. And looking at this at a larger scale, say a landscape scale, these requirements can be scaled up to be represented by things like fire weather, the general type of vegetation that's present, which then leads to the different types of fuel. And also, again, ignition sources. For example, human ignitions based on agriculture fires, arson, accidental ignitions, or natural ignitions like lightning, or to a far lesser extent, volcanoes, for example. And this can also be described in terms of the changing relationship between humans and the different elements of the fire triangle I just described. So starting from the natural ignitions on the very left-hand side, we then move forwards in time, closer to the present day, where humans have a much larger role to play in terms of their impact on the agricultural land management and the related impacts on fire, all the way to managed fire suppression in the current day and age, and also the climate change, which influences the existence of different types of vegetation and also the different fire weather, which then leads to the different fire seasons, of course. Many studies have looked at changes in fire season over the years, and this is something that is, again, very relevant in terms of our empirical analysis. Ecologically speaking, there is also a very large significance of fires, of course. I think a study that illustrates this quite nicely was actually done all the way back in 2005, where they looked at the impact of fire on global vegetation distribution using a coupled vegetation model. What you can see is that on the bottom map, where fire has been turned off, the extent of trees, the green cells, is much enhanced, which means that the distribution of vegetation currently, especially the grasslands, say in Africa or in South America, are to a very large extent controlled by fire and regulated by it. So that's just one of the massive ecological impacts of fires. So in addition to these impacts, of course, wildfires are affected by climate change, as I mentioned previously, but fires also have an impact on the atmosphere and on the future climate in that respect, just because of the different emissions of fires like greenhouse gases and aerosols. And of course, fires also have huge socioeconomic impacts, health impacts, economic impacts, all the way up to loss of life, unfortunately. And what we need to understand the future consequences of fires in respect to climate change are wildfire models, especially coupled wildfire models, because those are required to represent all the different feedbacks between fire, the atmosphere, and the biosphere, for example. What's important in these models in terms of accurate wildfire depiction is accurate weather prediction in the short term. Again, this is the aforementioned fire weather, which causes drying of fuels in certain months and therefore very high flammability and therefore high burnt area. And in the longer term, we want to look at climate properties and other biosphere properties like soil properties, which affect the vegetation distribution, because this does have a large impact on the types of fires that are present. Now, what's appeared in recent literature is that the relationship between the seasonality of burnt area and the seasonality of vegetation is still not as well understood as the relationship between climate and fire. So this is something that we especially wanted to focus on in our analyses. Just to illustrate how this actually looks in practice on a global scale, we can look at the seasonality of burning in general. Again, you can see that looping through the years, there are many months and many clusters around these months where fire is the most intense. So this can be seen very clearly in the Sahel region, in Africa, or in Northern Australia, for example. And these regions where fire is very seasonal, these are also regions where vegetation is very seasonal as well. So it is especially these regions where the study I will talk about soon has the most relevance. And just for context here, we can look at the same thing for vegetation, where again, we can see that in the aforementioned regions where fire fluctuates very largely, there's also an associated fluctuation in vegetation growth. You can contrast that with the behavior in tropical forests, which tend to remain largely the same, showing that there isn't much of a large seasonality there, as you would expect, and that is partly the reason for the lack of large fires in such areas, barring, of course, human influence. So the way we went about modeling this was, of course, to select a range of fire-relevant biophysical variables with a particular focus on vegetation variables. We then shifted these variables to investigate antecedent effects. So this was done for the 4 different vegetation proxies that were included, as shown here, and also for the dry day period, which of course was included to measure the drying out of the fuel. We used random forest modeling, and this allowed us to, of course, model the relationships between the different variables, but also to quantify things like feature importances and much more. In terms of the different vegetation data sets that were included, they all capture different aspects of the underlying vegetation, with some, for example, the VOD being more sensitive to woody biomass, i.e. in forests, whereas others like the FAPAR or LAI, which are highly related, capture more of the highly seasonal biomass like grasses or shrubs. So at a large scale, we can show all of these variables as a little map here, where we've got the climate variables on the left, including the soil moisture, but of course also including more common variables like the temperature. And then in terms of the ignition sources that we wanted to represent, we included lightning, population density, and cropland cover. To represent the different vegetation types, we included different land covers, so from shrublands all the way to herbaceous vegetation, above ground biomass, and then of course the 4 aforementioned remotely sensed vegetation proxies. And these were all linked together using the random forest modeling approach. We also had to do some processing, of course. So not all of the data sets are available at a monthly resolution, which is the resolution we carried out our analyses at. And they weren't all available at the same grid scale either. And this was simply averaged to get the same spatial resolution. Or in terms of temporally static data sets like the above ground biomass data set, they were recycled, i.e. the same value was used for every month. But what is of particular importance is that there are significant spatial gaps across different times, especially in the northern latitudes. And that's something that I will talk about a bit later on, because that is one of the big caveats in the study and in the study of fire in general, because in these boreal regions in the northern latitudes, it can be difficult to record the requisite variables that are required. In terms of the actual machine learning approach and data processing, we did climatological averaging, as you can see in the bottom left. So this means that we took the 5 or so years of data where all the different data sets were available, and we averaged them to be a representative year. We also, as previously mentioned, shifted the variables. So that can be seen in the light blue curve, where we essentially look at the state of the variable a couple of months before the fire, if you will. In terms of the random forest models, as previously mentioned, they allow us to calculate the importance of individual variables. But by carrying out different modeling experiments with different sets of variables, we also get a different view into the importance of the individual variables. And of course, using other techniques, predominantly the ALE technique, accumulated local effects, we are able to look at underlying relationships and interactions between the different variables as well. Now, accounting for the missing samples is a tricky question just because the data gaps are so pervasive in the northern latitudes. So as you can see on the right-hand side, there are very large regions where data is missing. And this was filled in two ways. First of all, the winter months, where there were persistent gaps in some of these properties, were filled using the minimum value observed at that location. And the remaining gaps were filled using something called a season trend model, which is a linear trend coupled with a Fourier decomposition of the remaining samples. So an example of that can be seen here, where you can see many of the samples are simply filled using the minimum value. In fact, 21 of those in this time series. And some of the samples were also filled using the orange curve, which is this season trend model I previously mentioned. And you can see that this in general does a pretty good job of representing the seasonality of the variable, which is our primary concern, because other variables like the temperature, for example, will in effect provide the information that it is currently winter, say, and fire is unlikely. And therefore, the properties of the vegetation during that time period is less relevant than it would be otherwise. In terms of the target variable of our analysis, the burnt area, we used one data set, the GFAD4 data set, but that is of course not the only data set that is available. So this study here in 2016 on the right-hand side looked at different burnt area data sets and the disagreement between them. And looking, for example, at the topmost plot, that's the variability in the mean burnt area. And you can see that the agreement is highest where burning is highest. So these two clusters in Africa and in Northern Australia feature the highest agreement, or the lowest variability in this case, whereas all the other regions have an incredibly high variability, even just in the mean. And if you look at other properties, such as the temporal slope at the bottom, we can see similar disagreements. And one of the main reasons for this is, of course, the fact that the satellite sensors used have difficulty measuring very small things. And in this case, that will then impact the detection of small fires. So that is a big reason for discrepancies, especially in regions dominated by agricultural fires. And another reason is simple limitations of the sensors used and the type of detection, i.e. passive measurement, which is impacted a lot by cloud covers. So on the left-hand side, I've plotted the percentage of, or the number of observed months where there has been no cloud cover. And we can see that especially in tropical regions, that number is almost zero. So across these 7 years or so, we can see that especially in the tropical regions, there is very low data availability. And this then, of course, hampers the accuracy of the data set. And in the future, there might be other data sets that are able to overcome these limitations, better usage of different sensors and different measurement types, like active fires, could remedy these issues to a certain extent, but it's certainly one of the limitations of such studies currently. Just to give an example of the small fire deficiencies, this is a study from over China. And you can see on the right-hand side that the actual fire occurrence is far outmatches the actual detection of fire on the very left-hand side. So this is a region that is, of course, very prominently populated with agricultural fires. And this is a problem because they tend to be rather small. Another problem with agricultural fires is that they tend to be, the timing of burning tends to be mischaracterized. For example, here we see that the burnt area at the top is apparently occurring far before the actual burning has occurred. And that's, in this case, likely due to the fact that the harvest of the crops causes such a reflectance change that it's misinterpreted as a burnt area. And the bottom two rows, they actually look at thermal emissions, so they're unaffected by this artifact. That's just another one of the difficulties associated with burnt area measurements. Right, now, given all these caveats, the results of our study are encouraging if you look at the spatial patterns. So the reproduced, i.e. predicted burnt area by our model is seen in the second row, whereas the top row shows the observed burnt area. And these are all out of sample results. So this is data that the model has never seen. And what's also apparent, however, is that the low burnt area regions are not reproduced as well. Of course, bear in mind that this is a logarithmic plot. So we have a very large range in orders of magnitude between grid cells that burn and grid cells that burn very little. And this is something that the model currently struggles with. So generally, there's an over-prediction of burnt area. We can visualize this another way using these histograms, where on the very right-hand side, we see that the model does not predict as many large fire events as are observed. And on the very left-hand side, we can see that it also doesn't predict as many grid cells without any fire as are actually observed. And this is by no means a surprise, really, because this kind of bias or compression, or whatever you want to call it, is rather common with these models and something that, well, could be compensated for, but it's just something to note for the later results. So in terms of the feature importance, it is essentially a way to calculate how much each of these features contributes to the final predictions and how important they are, of course. And there are many different ways to calculate these, and we've chosen to focus on 4 of them. So the Gini importance values, the permutation feature importance, leave one column out, and SHAP values. And then, of course, also the models with different sets of variables, which also tell us about the importance of the variables contained therein as well. Now, as you may imagine, these different metrics, they all have different advantages and different downsides, and they actually yield rather different importances as well. So as we can see here, if we average all the metrics, we get the ordering that is seen here, with dry days being the most important variable, followed by the FAPAR, which is again the measure of vegetation greenness, followed by the maximum temperature. Now, intuitively, these are all variables that we would expect to be very important. And in general, most of the metrics agree that these are important. However, the local importances, the green squares, do not agree in all cases. So there's definitely a large amount of disagreement here. And what the exact reasons for this, I'm not too sure about, but it's certainly interesting to see how much of a discrepancy there could be if one chooses to focus on a single one of these metrics in isolation. And looking at different sets of variables, we can see in general that the inclusion of antecedent variables, so looking at the history of different variables, improves the predictive performance. So we've got the training performance on the orange crosses, and the validation and out-of-bag training scores in the blue and green triangles. These X labels refer to the different sets of variables. And on the very right-hand side, we have a model that is simply the combination of all the 15 current variables. So this does not take into account any antecedent effects, whereas moving to the left on this scale, we include more and more of these antecedent effects, where on the very left-hand side, we have the all model, which actually contains so many shifts that it rises all the way up to 50 variables. So that's 35 more than on the very right-hand side. And there's a corresponding increase in performance. And if we look at the best 15 model, for example, that only contains 15 variables, but performs pretty much as well as the best model here, indicating that, of course, many of these variables will be correlated and contain the same information. Therefore, removing the extraneous ones, as we did there, does not really affect the performance. In general, it's interesting to note that the validation performance rises to a quite high extent compared to the training performance. Although it has to be noted that the training performance was already quite high and doesn't really tell us much in the first place. So in general, we found that the dry day period, maximum temperature, and the FAPAR were the most important. And out of the different vegetation variables that we looked at, the FAPAR was the most significant. And this makes sense if you consider the types of fire that our study is most likely to focus on, and something which I'll talk a bit more about in a minute. We did find that antecedent variables from 1 or more years ago were not significant, which is also true for the tree cover, the above ground biomass, and the lightning ignition. So those were not significant at the global scale we investigated. One of the more interesting results that we arrived at was the fact that there are these intuitive and consistent differences between instantaneous and antecedent relationships. If we look at the relationship between the instantaneous FAPAR and burnt area, you see that it is negative. So increasing FAPAR yields a decreasing burnt area. And this is because FAPAR is highest during the wet season, where the fuel is not dry and therefore not likely to burn. We see the opposite behavior looking at antecedent months. So if there is high FAPAR 1 month before the fire, statistically speaking, that's likely to increase the amount of burning. And that's simply because in this case, there'll be vegetation growth before the fire, which could then lead to increasing fuel buildup during the fire and therefore increasing burnt area. And this pattern continues all the way up to around 6 months, after which the behavior reverts back to the instantaneous relationship due to the large yearly autocorrelation. So the FAPAR in the current year would be quite similar to the FAPAR in the previous year, at least at the very large grid scales we investigated. And so that's the explanation for that reversion of the behavior. And for the dry day period, we see the opposite behavior, where the current month's dry day period has a positive effect. So this is to be expected. If it's currently dry, then you would expect an increasing amount of fire. And for the antecedent dry day periods, we also see, again, a mirroring of the relationship, where an increasing dry day period in previous months yields decreasing vegetation growth, which then causes decreasing fuel loads and therefore decreased fire. At the very extremes of dry day periods, so on the very right-hand side, for example, we see that there is an increasing relationship once more, however, and that's true across all different timescales. And we believe this is due to the effect of extended droughts on fuel dryness. And for example, if you have a very long drought It will dry out different kinds of fuel, not just grasslands or shrublands, which tend to dry out very quickly, and therefore it has the potential to cause very large fires. One note about the technique that I just used, which was the ALE plots. What is most commonly done in the field are PDP plots, which essentially show the partial effect of one variable taking into account all the other variables. The ALE plots do much of the same thing, except they are a more statistically rigorous way of doing so. And just to show the effects of the slight change in methodology, we have the same variable being plotted on the right-hand side, once with its effect calculated with the ALE technique and once with the PDP technique at the bottom. And you can see there is a difference. And this is because the ALE technique does not actually extrapolate to unlikely samples outside of the input distribution of training samples. And this difference means that especially models like the random forest, which are not designed to extrapolate, will not perform predictably and will therefore lead to sometimes counterintuitive results, like we see in this case here. For other cases like this one here, in general, there is not much of a difference between the two techniques, but using the ALE technique gives a higher amount of certainty and reliability. What is interesting, though, is the amount of inhomogeneity present in these relationships. We can see here that if we subsample the data sets, and this is something that you would do to get something akin to the ICE plots on the right-hand side, we see that there's a large amount of differences in the relationship, also referred to as inhomogeneity. This signifies that the relationship may change depending on which part of the globe you're looking at, or even which time you're looking at, something that is also apparent for other variables and at other timescales. And another interesting thing to look at with the underlying relationships is the fact that if we only include the current state, we sometimes get different behavior for the models. So if you look at plot B here, for example, we can see that the blue curve is first rising and then falling, whereas what we would expect for this kind of vegetation variable is a strictly monotonic decrease, like we see on the left-hand side in plot A. And this just shows that if we don't include all the relevant variables, which in this case includes the antecedent variables, we are likely to get inaccurate relationships between these underlying variables and the resulting burnt area. Regarding the aforementioned inhomogeneities, one way to explore the reason for these different behaviors is to look at the different interaction plots. And in this case, here we can look at two-dimensional interaction plots between two variables. In this case, population density and FAPAR. And we can see that there is a positive effect on burning in the lower left-hand side, meaning that for a low population density and a low FAPAR in the current month, we experience increased burning as a result. And this makes sense because at high population densities, we expect to have higher fire suppression, i.e. less resulting fire. And similarly, for a higher FAPAR, we expect there to be less burning due to the wetness of the fuel. What's interesting to note here, of course, is that there seems to be an interaction going on between these two variables where there is an additional positive impact on burning when these two variables are low. And this is also something that can be seen for the FAPAR variable. So if you look at FAPAR in the current month on the x-axis and FAPAR in the previous month on the y-axis, we can see there's an interaction for low current months FAPAR and high antecedent FAPAR. Now, individually, this is also something that we've seen before in the underlying relationships, but it's interesting to note that this interaction here indicates that high FAPAR in the current month, or the impact of FAPAR in the current month, is conditioned upon the FAPAR in the previous month, which means that only if the FAPAR in the previous month is high does a low FAPAR in the current month yield the increased burning that we saw previously. Note, however, that this interaction is relatively unlikely because, as you can see on the right-hand side, the two variables, so the current month's and last month's FAPAR, are highly correlated. There aren't many locations where you would get this interaction, which is why there aren't that many regions in the world with a very high burnt area. And we can look at the affected regions by essentially subsetting the original data and seeing what regions it applies to. So here we have an example of an interaction between maximum temperature and lightning. And we see that for a high temperature and high lightning, there is increased burning. And this applies mostly in Northern Australia. Another interaction with lightning is yet again very active in Northern Australia, but also in parts of Africa and South America. And we can use that to essentially illustrate where these different variables are important given their different interactions. And another way to look at the spatial location of these different effects is to look at the SHAP values, which allow us to calculate the importance of certain variables at each grid cell and also at each different month for a given grid cell. We can use this to calculate the most important month for a certain variable, like we did on the right-hand side, where we see that in tropical regions, for fire, it is most important what kind of vegetation properties there are in the current month, so very close to the fire. Whereas in other regions, it's rather more important what happens a couple months before the fire. And this just hints at the fact that in regions where vegetation state before the fire is most important, we have this high seasonality, where the fire is sensitive to how much vegetation was growing a couple of months before the fire, which then might have a chance to die and then become fuel for the fire. And we see something similar with the dry day period on the left-hand side, where the most important properties are in general the dry day period in the current month. So in tropical regions, that can be seen to have a generally negative impact on burning because it tends to be wet. Whereas in other regions, shown in orange, it tends to have a positive impact because during the fire season, it tends to be rather dry there. We can do this in greater depth with other variables as well. And in general, the aforementioned discrepancies hold where there is one relationship in the tropical regions and another relationship in regions with a more seasonal vegetation, generally grasslands and shrublands. So what have we learned from this analysis? We've taken many different data sources, applied our machine learning techniques to it, and we found that in general, the FAPAR variable is most important. And this can be linked to the fact that our analysis responds strongly to seasonality, which is most apparent in shrublands and grasslands in the world, which FAPAR is most sensitive to, as compared to some of the other vegetation properties I included, like the VOD. There are significant interactions between variables, significant differences between the instantaneous and antecedent relationships, and also different times and different lag times that are significant for each of the variables. So the different instantaneous and antecedent relationships can be seen here with the FAPAR example. And the different timescales of importance can be seen here again with the discrepancy between the tropical regions that respond more strongly to instantaneous conditions and the other regions that respond more strongly to antecedent conditions. So in terms of applications, the INFERNO model that was developed at Imperial is the sort of culmination or application of the relationships that I just talked about, is the culmination or culminate in application to the INFERNO model, which is schematically shown here. Specifically, what we want to do is focus on the burnt area prediction and the associated flammability. Something that is a little bit irksome at the moment with the INFERNO model is that to circumvent fire spread modeling, which at the coarse scales the model is run at is rather hard, it is presumed that there is a certain typical burnt area per fire for certain vegetation types. And that is something that could potentially be remedied by accounting for the relationships that I just mentioned. And again, in the grander scheme of things, in the whole vegetation model and land surface model, we are looking at improving the circled component that deals with the fuel loading and then also the different fires that result from this fuel loading. One particular focus is, of course, the flammability, where previously it was based on things like temperature and relative humidity. And we are currently exploring alternative parameterizations based on things like maximum temperature in a month or the antecedent productivity. And different ways of parameterizing dryness would include something like the dry day period or a mixture of VPD and precipitation. And we're also looking at different literfall metrics or antecedent productivity to better parameterize fuel buildup. In particular, the way we're trying to achieve this is by using a kind of generalized sigmoidal relationship, where we want to fit PFT-specific relationships to each of these variables, and then combine them multiplicatively to yield the final flammability. And this is, of course, a very generalized technique that's able to be fitted using the available data. So it's a kind of parametric approach to fire modeling from an empirical standpoint. If we look at the performance of this kind of new parameterization, we can see that the phase performance has been improved. So looking first at the observations on the top left-hand side, we see that in terms of the phase of the burning, so the timing, it has a very skewed timing when we compare the INFERNO model as it was beforehand at the top right-hand side to the observations in the top left-hand side. Whereas if we look at our new parameterization, we see that especially in the northern latitudes, we've managed to account for the timing of the burning much better. And this is again apparent by looking at the mean phase difference metric that you can see here, where the old INFERNO does not score as well. And in a similar vein, the prediction of the actual magnitude of burning has also been improved in the northern latitudes, where we can see the different performance on a grid cell level basis here, where on the bottom right-hand side, we see the lower errors at the top in the northern latitudes. So yes, in general, we've seen that prediction of burnt area using this kind of empirical analysis methods and machine learning is rather successful. Looking at the top left plot here, we have a broad reproduction of the general geographic patterns. And we also found some interesting relationships between variables, such as the difference in instantaneous and antecedent relationships as seen in the bottom plot. So yeah, if you have any questions, please let me know, and thank you for your attention.
Thank you, Alex, for the very nice talk. I found it's very clear and inspiring. So for the audience, in case you have any questions, please either raise your hands and unmute yourself, or you can leave your questions in the chat and I will read it out for Alex. So at the same time, in fact, I have several questions. I think I can start. So the first, I think at the beginning, you showed that just before, after fire, there's a significant change in terms of the vegetation. I think at the beginning, maybe third or first slides.
Let me go back.
You should fire off. Yeah, before that, I think. Oh no. Yeah, so I think as at the point you said that the fire can be seen as a regularization of the vegetation.
Ah, oh, right. I see. I think you're probably referring to this slide.
Yeah, exactly. So my question is just, I mean, from my point of view, like I see many like fire simulators, they use the vegetation as the input to predict the fire.
Mm-hmm.
But I think here what you suggest is actually the fire will give a very big impact on the growth of the vegetation afterwards. So do you think these, so firstly, I find this is a very interesting point. And do you think this is something that you can predict also with, for example, a similar approach you used here to predict the BA? Or it would be more challenging?
I mean, it would be challenging because the outcome that we're looking at here is a result of the different interactions between vegetation, climate, and fire. So, I mean, really the best way to look at this is the way that they have done here with these integrated fire models, well, the fire models integrated into the vegetation models. And ideally, you'd want to couple it to a climate model as well, of course, and go about it that way. And I mean, otherwise, I think it's going to be rather difficult to consistently determine the effect of fire on vegetation distribution, just because, I mean, of course, currently this could be done by establishing a connection between, let's say, the climate state and the vegetation distribution, and then saying that there is some mediation by fire involved in this. But given changing climate, for example, that relationship may no longer hold, and that's that could be a problem. Yes.
Yeah, so you're suggesting that there are more like inputs that we need to take into consider to that.
Yes, I mean, ideally, this kind of study takes into account the different fire adaptations of vegetation, just because the way vegetation responds to fire is, of course, dependent on how tolerant the vegetation is on fire. And yeah, I mean, that's not something that is currently represented well in most vegetation models. But I think from a purely sort of non-interactive empirical or machine learning standpoint, it might be quite difficult to account for all the different feedbacks. Yeah.
Okay. Thank you, Alex. And I see there's also a question from the audience, from Cesar. So hi, Alex, have you explored deep learning models or other methods, not necessarily tree-based methods? Are tree-based methods used because of their explainability?
So yes, that is one of the primary reasons that this method is quite popular. It's also relatively easy to fit them. And the fact that they are quite explainable is a plus, but of course, we are not, with the exception perhaps of the Gini importance metrics, we're not really using many of the explainability features just because we're growing such deep trees, and it wouldn't really be feasible to look at the actual underlying decision trees in practice. And many of the techniques that we use, like the ALE plots, or the SHAP values, etc., could be applicable to other methods too. With the caveat that, for example, for the SHAP values, there is a much improved implementation based on on code that is written specifically for tree-based models. So that is actually one advantage of using them here. But similar studies have used something like MLP models and other kind of machine learning models to do similar work, albeit with different focuses, of course. So the choice of machine learning model is by no means necessary, but it did have several advantages in our case.
Okay, thank you, Alex, for the clear answer, and thank you, Cesar, for the question. So let's see if there's other people who ask the question. So Cesar, just would like to thank you.
Yeah, thank you.
If not for a moment, actually, I have another question. So I saw when you use the random forest model, you're actually using the data from the models. So yeah. I'm supposing that these are the data they're spatially distributed, right, as the vegetations or the densities. So when you use the random forest, do you use the random forest to include image data sets, or you use some like feature extractions from these images? I mean, by images, I mean the spatial distributed data to process the regression.
I mean, we're just using the raster data sets here. So we have the 1440 by 720 images, essentially, or I'm not sure you can call them images, but data sets as such. So they're essentially just a equirectangular projection of this 0.25 degree data set, which it brings along its own issues, such as the unequal areas between grid cells, but this is quite a common technique and computationally convenient. Yeah.
Okay.
I'm not sure if that answers your question.
Well, actually, if I go a little bit further, it's like so when you use like these data as your input, you take every pixels in the multi-dimensional data as an individual input, or it's like okay, I see.
Yeah, so we're not, looking at different fire events, if you will, like in the fire atlas. We're just looking at different pixels after they've been averaged into the sort of climatological representative year and looking at the different input properties, pixel by pixel and month by month. Yeah. Okay. So, I mean, of course, I guess what you're asking about is also relevant for something like temporal networks, like I'm not sure this is the right name, recursive nets.
You mean maybe recurrent neural network?
Yes, the ones that essentially take into account antecedent information. The one, you can apply them for time series quite readily, but that's not something we chose to do here just because we looked at these shifted variables as well. So that was our way of including this kind of antecedent information.
Yeah, and I think that, as you suggested, maybe your model is have a strength in terms of interpretability compared to the deep learning model.
Yeah, I think with the sort of RNNs, it's perhaps, although I'm by no means an expert, it might be a bit more difficult to extract underlying relationships with specific months like we've done here.
Okay, thank you, Alex. So actually, I have a final question if there's no questions from the audience. Okay, so I have a short question. So I think you have shown your model for the prediction like per year or per month. Do you think it's possible to do that in a more like short prediction term? So for example, per week or per day, or that would be too challenging?
I think it would be rather challenging just because it's tough to get these predictions right even on a monthly timescale if we average different years. And so that is this climatological time series I've been talking about. And we did actually look at performance on unaveraged years as well. And, unsurprisingly, just because we're not averaging data, which means we have a higher variance to account for, there was a lower performance. it was still decent, but even just moving from a representative year to an actual time series across many years results in a decreased performance. So I think moving all the way to weeks or months based on this data at these scales would be rather challenging. Yes.
Okay. Thank you, Alex.
Thank you. Yeah.
And if let's see if there's a final question from audience for Alex. So if not, actually, we're quite close to 5 p.m. I think we can close the seminar today. So I'd just like to thank you again for Alex to give a nice presentation. And thank you everyone to attend today's seminar. So yeah, so have a nice evening to everyone. And thank you, Alex.
Thank you.
Bye-bye.